We've looked previously at embeddings and the embedding metrics. Now let's look at the Word2Vec model from which high quality embeddings could be extracted, and this high quality embeddings could be used in other problems. Hence, this could be used for transfer learning. Talking about transfer learning, recall we had seen with convolutional neural networks that we could build a model, or we could train a model on some input data. Then later on we could take in the first layers of this model and use it as a feature extractor on some other data different from the previous input data. Just the same process could be repeated with text data. Recall that the role of the embedding metrics is simply to take the data from a high dimensional space to a low dimensional space, or a relatively lower dimensional space, in which similar words actually occupy positions very close to each other. Now that said, what we'll do is we shall train a model which contains that embedding metrics, and then after training this model on very large data sets, that embedding metrics will be used on other different tasks. Let's look at ways in which we train this initial model from which the embedding metrics will be extracted. Supposing we have an input of vocabulary size 3 million. So what we're saying here is we have some input words which are part of a 3 million vocabulary, or part of a vocabulary with 3 million different words. The aim of the embedding metrics is to convert this into a lower dimensional space, like say 300 dimensional embedding space. And just like with convolutional neural networks, where we train on millions of images for the ImageNet in particular, here we shall also train on very huge text data sets. Now let's suppose we're working with a huge text data set and that will extract just this small portion from it. What goes on here is we could use an n-gram model based on neural networks. So from this we'll pick out, let's say 1, 2, 3, 4 words, and then the model takes as input the first 3 words, and then the model tries to predict the next word. So as you can see here, we have look into the first 3, so we have 3 inputs and then 1 output. This problem is actually a next word prediction problem in which we given some previous words, hence the term n-gram. So if we're dealing with 4 words, it's a 4 gram. We're dealing with 2 words, it's a 2 gram or a bigram. If we're dealing with 5 words, it's a 5 gram. So this kind of data set could be obtained from a book or from some sites like Wikipedia, which contains huge text corpus. As you could see, this just corresponds to the first data point. The next could be constructed by simply sliding this window to the next position. So we could have now into the C and. In this case, our inputs will be into the C and our output will be and. Then we'll slide again to the C and tell. Inputs will be the C and our output will be tell. We repeat this throughout the whole data set to recreate this new data set right here. Once this is done, we can now build this kind of model. This model takes as input the 3 words, and then each word is a 1-hot vector with 3 million different positions. Then after going through this embedding layer, what we obtain is this tensor in which each of the words is represented by 300 different positions in a feature vector. So we'll see how we'll live from 3 million to 300. Then once we get this, we could simply flatten this out. So we have now this 3 by 300, which gives us 900. So when you tensor has shape batch size by 900. Then we get through a dense layer which will permit us classify, or better still, choose between the 3 million different words we have in our vocabulary for the output. Because what we're trying to solve here is we're trying to build a model which, when given these inputs, will rightly predict this output. Now we have 3 million different possibilities, so that's why we have the softmax, and then we have this dense layer with an output of 3 million different positions, so that we could pick one out of these positions. After preparing this data set like this, we simply pass this in and train the model. But there's a problem with this way of training this kind of models. The softmax is defined such that for each position we have the exponent of, or e to the power of, the value obtained in that position divided by the sum of all the different other positions, or the sum of all the exponents of the values we obtain in the different positions. Now the sum for very large vocabularies is very computationally expensive, hence this method is very inefficient, even though after training we'll be able to extract this embedding and then use it on some other task. But due to the computationally expensive nature of this method, the Word2Vec algorithm was developed by scientists at Google. So suppose again we have an input data set. Also note that generally data sets contain a huge number of text corpus. Now if we take out just this part from such text corpus, we could also break this into a frame. So we're taking this frame of, say, n words, and in this frame of n words, for each word in our frame we could have, for example, we pick out the C. We are gonna have an input, or as input C, and then as output words from this frame. So like in this case we have C, we have the word the, we have C again, the word into, C the word and, C the word tell, C the word me, C the word what. This we could call positive samples because these outputs belong to the same frame as the input C. Now for each of these data points, that is for example C there, we are going to generate negative samples, and the number of negative samples is actually a hyperparameter. So in this case, for example, we've chosen, say, 1, 2, 3, 4, 5 negative samples. So for each positive sample we have this 5 negative samples. Now how do we create these negative samples? We have, for example, C, we pick out a word at random in the whole text corpus. So supposing we have a text corpus of millions of, or even billions of different words, then we simply pick at random a word from that text corpus. And even if this word happens to fall in this frame right here, there's no problem, although it's actually going to be very rare. So in our case we have C, we pick out a word, say hello, pick C, a word, say uncle, C daily, C fan, C me. Now note that this data set and this are going to be concatenated together. So in this case we have the C there, which the C there, and then we have the C's with this negative samples. We do the same for the C into, where for the C into we have 5 other points where we have C linked to some random word in the text corpus, and this is repeated 5 times. We repeat this up to C what. We see that for this we have C linked to 5 other negative samples in the text corpus. And then if we have to concatenate this positive sample with the 5 negative samples, we'll obtain this kind of data set wherein we have the C there followed by the negative samples, we have the C into followed by the negative samples, and so on and so forth. Then once we are done with this window, we slide the window to the next position. So now the window is gonna have the, see, and tell me what, and you. So we'll get from this point to this point. Then again, we could pick out a third word, just like we did in this case, in the window, and then repeat the same procedure. By doing that, we'll generate hundreds of thousands and even millions of data points. Each of these data points is passed into this model, which starts with the embedding layer, then the flatten, and then a dense layer with sigmoid activation, unlike here where we had a softmax activation. The actual difference between these two models is that apart from the fact that the input is just one word, unlike here where we had 3 inputs, in this model, for every input, like say C, the loss is computed based only on these words here, which are linked to C in the data set. Now what does this mean? It simply means that if the input is C, then out of this 3 million elements, we are only going to work with or compute the loss for all these words which in the data set are linked to C. So wherever we have the word C, so supposing we have the word the, for example, and this position in the vocabulary is say the second position, then it means that at the second position we shall compute a loss between what the model actually predicts at that position and the expected prediction, which is equals 1, since this is a positive sample. Then for hello, uncle, daily, fan, me, baby, crisis, sleep, sound, and all the other negative samples, the expected output is going to be equals 0. For the and into with and, tell me what, the expected output will be equals 1. So this means that instead of carrying out or computing the loss based on this kind of computation where all the words in the vocabulary come to play, here we just focus on the positive samples and the negative samples. And so we are actually having a binary cross entropy loss where we could divide this into 2 parts. For the negative samples, we have the prediction by the model and the value 0, because normally it's supposed to be 0. That's the actual or expected target value. And then for the positive samples, we have the model's output and the expected value of 1. This means that in this example, if we take this to be 1 positive sample and 5 negative samples, then we'll have 6 data points generated on this first. Here 6, 6, 6, 6, 6. Then we shall have 1, 2, 3, 4, 5, 6 by 6. That's 36 different positions in which we're going to carry out binary classification, unlike in this example where we're carrying out multi-class classification for all 3 million different possible words in our vocabulary. Now once we're done with training, all we need to do is to extract this embedding matrix right here, as it should have learned how to get this kind of input in this 3 million size vocabulary and then convert it into very rich, high quality embedding features, obviously of lower dimension. And in the practical session, we shall see that once we've gotten this kind of embeddings and we know exactly, or we have a set vocabulary, we wouldn't need to build this vocabulary again. All we need to do is to use the same vocabulary which was used in generating this embedding matrix right here.